converter with RLE load and freewheeling diode. Okay, so last class we discussed single phase half wave control with R load, RLE load, and okay, R load, RL load, and RLE load. But here we are discussing single phase half wave controlled converter with with RLE load and also freewheeling diode. Okay. Half-wave controlled converter with RLE load and a freewheeling diode. Here you have to see this diagram. Okay. Here single phase half wave control. So half wave control means the circuit diagram will be two thyristors and two diodes will be there. And here this is a freewheeling diode and load will be RLE. Okay. So resistance, inductance and a battery. Okay. So whenever we are giving a gate pulse, then the gate pulse will be given to T1, then T1 D1 will operate. At starting T1 D1 will operate. So whenever and again T2 we have to given gate pulse to T2, then T2 D2 will be operate. Okay. Here the current flows from source to T1 and T1 to RLE load and T1 to load and D1 and it will goes to this. And whenever we are giving a T2, so here so in this gap, so to start T2, in this gap here freewheeling diode will act as a circulating path. Okay, and after that whenever we are giving a gate pulse to T2, then then T2 D2 will be okay. Here T2 D2 will be operating. Okay. So starting T1 D1 will operate and T2 D2 will be operated. So single phase half wave converter with RLE load. Half wave control means here two thyristors and two diodes will be there. This is a freewheeling diode and this is a load. Okay. So at starting we are giving a T1, then T1 D1 will operate and whenever we are giving a T2, then T2 D2 will be operating. Okay, so when we have to see the waveforms, here this is a source voltage. So this is source voltage and this line will be battery. Okay, so E. So this load E. Okay, so VAB, VBE, these are the source voltages and this will be E. So E battery of voltage. So whenever we are giving a pulse, so whenever we are giving a gate pulse T1, then operate T1 D1. Okay. So at uh, at an alpha we are giving a gate pulse to thyristor, then the waveforms will be going like this. Okay, so V naught will be like this. So V naught waveforms will be like this. It will comes to 0 at pi. Okay, and after again it will be increasing. We are giving a gate pulse to T2. Okay, this is the output voltage V naught. Okay, and output current will be continuous. Why? Because here freewheeling diode will be there. Freewheeling diode will be there. So the current will be circulating in negative cycle also. That's why the current will be in continuous mode. Okay. So next, the current, freewheeling diode current. Okay, here the freewheeling diode current. When freewheeling diode current will be means, so before starting the thyristor, the current in freewheeling diode will be flows. So before starting T1, the freewheeling diode current will be like this. And so, and whenever the thyristor will be on, the freewheeling diode current will be 0. And again it will be increases when thyristor when thyristor T1 will be 0. So, and before starting T2, the thyristor T1 will be, and the thyristor T1 will comes to 0, and before starting T2, there will be some gap will be there. Then that gap up, so the freewheeling diode current will be flowing. Okay, so this is a freewheeling diode current and source voltage. Okay, so source voltage means, so at starting the source voltage will comes to 0, and whenever the thyristor T1 will be, so thyristor T1 will operate, then the current will be flowing like this. Okay, so and it comes to 0 at pi, and again will increasing at pi plus alpha in negative direction, and it will becomes to 0 at 2 pi, and again it will be increases pi plus alpha. Okay, at pi plus alpha it will be increasing and decreases 3 pi and increasing 3 pi plus alpha in negative direction. So this is source voltage, and here thyristor T1 voltage. Okay, so the thyristor T1 voltage, so at start, so the thyristor T1 voltage will be 0, and it will be in after pi plus alpha it comes on minus Vm, and again it will comes to 0. So at so the thyristor will be conduction from 0 to pi plus alpha, and it will not conducting at 2 pi. So here the T2 will be conducting. This means here the thyristor voltage will be here. Okay. So VT2. So the second thyristor voltage minus Vm. So from alpha to pi, the thyristor T2 voltage will be there. Okay, so we have to see this is a single phase half wave controlled converter with RLE load and freewheeling diode. Okay, so next we have to see a problem. So single phase 230 volts 1 kilowatt heater is connected across the single phase 230 volt 50 Hz supply through an SCR for a firing angle delay of 45 degrees and 90 degrees. Calculate the power absorbed in a heater element. Okay, so the power absorbed in a heater element we have to calculating. Okay, so you have to see the solution. Heater resistance. So resistance means 20 voltage 230 volts square by, and here resistance R equal to V square by I. Okay, actually V equal to IR. Okay, R equal to V by I. Okay, so here 1000, here 1000 V 20 230 square by 1000 ohms. Okay, so 230 volts and 1 kilowatt heater. Okay, here 230 by 230 square by V square by here power. So R equal to V square by 1 kilowatt, so 1000. So power absorbed by the heater element for alpha equal to 90 degrees. So at 90 degrees V naught square R by V naught square by R. So here at 90 degrees the voltage will be uh, so at 90, so 90 means half of the voltage will be there. Okay, so 115 by here resistance will be 230. Okay, into 1000. Okay, so 1000 that will give 250 watts. And next, so the RMS value of voltage V naught R equal to Vm by 2 root 2 pi pi minus alpha plus 1 by 2 sine 2 alpha whole power 1 by 2. Here single phase, so single phase. Okay, so single phase wave. So single phase wave we have taken RMS value of Vm by 2 root 2 pi. pi minus alpha plus 1 by 2 sine 2 alpha. So we have to substitute these values. Then RMS value will be 155.071. So power absorbed by the heater element for alpha equal to 45 degrees. So V naught square by R. So here the voltage will be VM. So here the voltage will be substituting. So for alpha 90 degrees, the RMS voltage will be 115. When we have substituting these values, so it will be obtained 115 volts. Okay. So next, single phase full wave control rectifier. So single here today single phase full wave. So full wave means all R will be thyristors will be. So T1, T2, T3, T4 thyristors will be there. So this will be connected to AC supply, and we have to seeing the load resistance. So we have to seeing a resistance of load. Single phase full wave control rectifier with R load. Okay, so resistance load. This is a circuit diagram for single phase full wave control rectifier. Okay, so when you have to see the waveforms, so whenever we are giving a AC supply, then positive gate pulse will applying to T1, then the T1 and current flowing load and T2. So T1, T2 will be operated at positive half cycle, and at negative half cycle T3 and T4 will be operated. Okay, so T4 load and T3. Okay. So T3 will be. So in negative half cycle, T3 and T4 will be operating. Okay. So we have to see the waveforms. So three phase. So three phase means this is R and this is Y and this is B. We have three lines will be there. R, Y, B. Okay. So when we have to see this graph, the voltage. So the voltage. So whenever we are giving a firing pulse at at 20 degrees, so the voltage V naught will be like this. So it will be going up like this. Okay. Here, so in full wave rectifier, the voltage will be in continuous mode of operation. Okay. So in negative half cycle, T3 and T4 will be operating. So the voltages will be like this. So at alpha equal to 30 degrees, the output voltage. At alpha equal to 60 degrees. So at 60 degrees, the output voltage will be like this. So the voltage will be in continuous mode of operation in full wave. Okay. So at 90 degrees, the operating voltage will be like this. The output voltage will be obtained like this. Okay. So the voltage here we have to see this red color at alpha equal to 30 degrees and alpha equal to 60 degrees and alpha equal to 90 degrees. Okay. So we had this red color will represent output voltage for 90 degrees voltage. So in full wave the voltage will be in continuous mode and current also will be in continuous mode. Okay, so this is the waveforms for R load. Okay, so input and output waveforms for single phase full wave circuit with R load. Okay, next we have to see that so the single phase full wave control rectifier allows conversion of single phase AC into DC normally. This is used. So in various applications such as battery charging, speed control of DC motor and front end of UPS. So UPS means uninterruptible power supply and SMPS. So switched mode power supply. So actually single phase full wave rectifier we have to use so conversion of single phase AC to DC, and this is used in various applications such as battery charging, speed control so battery charging, speed control of DC motors and front end of UPS and SMPS. Okay. So all four devices used for thyristors. So here we are using four devices are thyristors. The turn on instant of these devices are depend on the firing signal. that are given. So turn off happens when the current through the device reaches to 0 and it reverse biased, at least for a duration equal to turn off time of the device specified in that data sheet. So in fast to half cycle, the thyristor T1 and T2 will be fired at an angle alpha, and T1 and T2 will be conducting. Okay, so here V naught equal to Vs and I naught equal to Is equal to V naught by R, and that implies Vs by R. So in negative half cycle, the half cycle of input voltage of SCRs will be T3 and T4. Here T3 and T4 will be triggered at negative half cycle at an angle of phi plus alpha. Okay, here opposite output current and supply current are in opposite direction. Okay, so output current and supply current are in opposite direction. So supply current Is equal to minus of phi naught. So T3 and T4 becomes off at 2 pi. Okay, so here V naught equal to 1 by pi integral of alpha to pi plus alpha Vm sin omega t d omega t. So when you have to simplifying this, the output voltage for single phase full wave rectifier will be 2 Vm by pi cos alpha. Okay. So next we have to see single phase full wave control rectifier with RL load. So resistor and inductive load we have to see. So here T1 and T2 will be conducting at positive half cycle, and T3 and T4 will be conducting negative half cycle. Here we have to use resistance and inductor load. Okay, so this is the circuit diagram for single phase full wave converter circuit with RL load. Okay, so we have to see the full wave converter circuit with R load. So and input and output waveforms. Okay, so this is a so we have to see this is a waveform. So the source will, so the output voltage will be obtained at an angle of alpha. So the voltage will be like this. So here, so the inductor voltage also will be attained, and here the current will be in continuous mode. Why? Because at starting T1 and T2 will be operating, and also inductor current will be flows. So that's why the current will not be zero. And this is the source current. And this is a thyristor voltages. Thyristor voltages will be like this. So the waveforms will be like this for full wave circuit with RL load. Okay. So next we have to see the operation of single phase full wave rectifier with RL load. So modes of operation we have to discuss in. So at mode 1 from alpha to pi. So from whenever we are giving a firing angle of at alpha, okay. So it will conduct from pi. So in positive half cycle is applied AC signal. So SCR T1 and T2 are forward bias and can be turned on at an angle of alpha. Okay. Load voltage is equal to positive instantaneous of AC supply voltage. So the load current is positive ripple. So free constant and equal to I naught. So due to positive polarity of load voltage and load current, and load inductance will store energy. So here, so positive polarity of load voltage and load current, the load inductance will store the energy. So at mode 2, so mode 2 means pi to pi plus alpha. At omega t equal to pi, the input supply is equal to 0, and after pi it becomes negative, but inductance opposes any, so changes through it. So in order to maintain constant load current and also in same direction, a self-induced EMF appears across the L as shown. So here in inductor a self-induced EMF will be induced to maintain a load current will be constant. Okay, So due to this induced voltage, so the SCR T1 and T2 are forward bias in spite the negative supply voltage. So the load voltage is negative and is equal to instantaneous of AC supply voltage, whereas load current is positive. So thus the load act as a source and stored energy in inductive is returned back to AC supply. Okay. So in mode 3, pi plus alpha to 2 pi. So at omega t equal to pi plus alpha, SCR and SCRs of T3 and T4 is turned on and T1 and T2 are reverse bias. Thus the process of conduction is transformed from T1 and T2 to and T3 to T4. So load voltage again becomes, okay. So the load voltage again becomes a positive and energy stored in a inductor. Okay, so T3, T4 conduct in negative half cycle from alpha pi plus alpha to 2 pi with a positive load voltage and load current energy gets stored. So in T3, T4 will be operated in negative half cycle, but with a positive load voltages and load current. That's why so the energy gets stored. Okay. So in mode 4, so 2 pi to pi plus alpha. At 2 pi, the input voltage passes through a 0. So inductive load will try to oppose any change in current. So if in order to maintain the load current constant in the same direction, induced EMF is positive and maintaining conduction of SCR and SCRs of T3 and T4 with a reverse polarity also. Okay. So thus the load voltage is negative and is equal to instantaneous of AC supply voltage, whereas the load current continues to be positive. So in 4 modes, the load current will be in positive mode. That's why the load current will be in continuous mode of operation. Okay. So thus the load act as a source and stored energy in inductance is returned back to supply. So at omega t equal to pi alpha or 2 pi plus alpha, T3 and T4 are commutated and T1 T2 will are turned on. Okay. So here V naught equal to 1 by pi integral of alpha to pi plus alpha Vm sin omega t d omega t. When you have to simplify this equation, then output voltage obtained will be 2 Vm by pi cos alpha. Okay. So next, single phase full wave controlled converter with RLE load. Okay. So the circuit diagram of full wave bridge rectifier using a thyristor is shown in figure. It consists of four SCRs which are connected between a single phase AC supply and a load. Okay. Here RLE load will be there. So here T1 and TT in positive half cycle and T3 and T4 will be in negative half cycle. Okay. So we have to see in this single phase full wave converter circuit with RLE load input and output waveforms. So at whenever we are giving at an alpha, we have to giving a fire impulse at fire impulse to T1, then T1 T2 will be operating. So the voltage will be the output voltage will be obtained like this. So here the output here the output voltage will comes to 0 at pi, but due to due to inductor and due to L and E load, so it will be storage of current, storage of energy will be there. So that's why the voltage will be comes in negative direction and it will be going like this. So this is a negative output voltage and the current will be in continuous mode of operation. Why? Because it is a full wave and the load will be RLE load. So there is no negative load current. Only positive load current will be obtained. So in full wave. Okay. So here this is a source. Source current will be obtained and the thyristor voltages will be obtained. Okay. So this is a waveforms for single phase full wave converter circuit with RLE load. RLE load. Okay. Next, we have to discussing the operation. So in positive half cycle of input, thyristor T1 and T2 are forward biased, while T3 and T4 are reverse biased. Okay, so the thyristor T1 and T2 are triggered simultaneously at some firing angle in positive half cycle, and T3, T4 are triggered in negative half cycle. Okay, so the load current start to flowing through them when they are in conduction state. Okay, so load current start to flowing through them when they are in conduction state. So the load for this converter can be R and RLE load depending upon the application. So by varying conduction of each thyristor in the bridge, the average output of this converter gets controlled. Okay, so the average value of output voltage twice that of half wave rectifier. Okay, so the average value of output voltage is twice that of half wave rectifier. Okay, here V naught equal to 1 by pi integral alpha to pi plus alpha Vm sin omega t and d omega t. When you have to simplifying this, the output voltage for single phase full wave rectifier with RLE load will be 2 Vm by 5 cos alpha. This is for output voltage. Okay. Okay. Thank you.